Okay, the pressure of NO plus the pressure of SO2, which is what we're trying to figure out, plus the pressure of water, plus the pressure of CO2. Okay, then it's just basic algebra. We're just going to subtract off all of those individual pressures off the 2.08. I'm not getting lazy. My back has just been bugging me and sore, so sorry. Okay, so I'm going to go ahead and subtract those off. You guys do it too so that you make sure you know how to do math and use your calculator. Okay, so I'm going to skip the next couple slides and go back to them just so we can stick with this whole partial pressures thing. So go to this slide. Okay. These three questions are meant to walk you through to get to the last question. So go ahead and start at the top, but let me just kind of explain what this is before we start. So you've got three containers that are kept separate by valves. So right now the valves are closed. They're trying to emphasize that by showing you the CO2 is just filling in that red space, the H2 is filling in that blue space, and the argon is filling in the gray space, okay? And we've got pressures and volumes for each of the gases listed below. And they're just for the volume of the red space, the volume of the blue space, etc. Okay? Then we're going to open the valves so that it's now one big container, and we're going to let all the gases mix together in that one big container. Okay, so that's kind of the setup here, and then it's going to walk you through these questions. So go ahead and take a shot at that as just kind of like an application of what we talked about. And you're going to have to apply some of the stuff we did earlier in the chapter. So I think it's good practice for that reason. Okay, so I'll give you a minute or two before I give you kind of some hints and direction as to how to approach this. As usual, go back to your notes if you're like, I don't remember what I'm doing here. Talk to your neighbor. Work through it together. After 3 hours in my insulated container, I think my tea is finally cool enough to drink. Why not just bring it in a regular cup, you might say? Because then it would be cold by the time I got here at 8:30 or 9 o'clock or whatever. First world problems, right? Is that a thing? Do people still say that? Yeah, okay. It's a little hard to keep up with what people say, and I'm a little tired of I don't even want to repeat it. The number thing, very, very tired of hearing the stupid number whatevers at home. Okay, so the biggest point to recognize is these are initial pressures and volume. Once I open up those valves, I now have a new volume, which is going to be just the total of all of those. So 1.5 plus 1 plus 2, so a total new volume of 4.5, which is going to change the pressure of the CO2 because it's now spread out into a larger container. So you've got to account for that in this calculation. Okay, when you're ready to check your work, it's up there now. So one big takeaway here is it doesn't matter if there's other gases mixed in there. You can still apply all the same rules to an individual gas within a mixture. Okay, that's a big takeaway. What about if I had asked, so I'm actually going to write this in so you guys can see. Isn't there a typey thing in here? Yes, there we go. Okay. How would you calculate the total pressure in the popcorn in the container once the valves, had been opened? Okay, so this is probably not that hard of a problem right now because this is not helping me to try to type these because now I cannot seem to select it. This is probably not going to be that useful or that difficult to answer now that you've already done it for CO2. Not sure why it won't let me do that. Sorry, guys. Okay, the question is supposed to say, how do you calculate the total pressure after the valves have been opened and all the bulbs can mix, all the gases in each 3 bulb, okay? So you can go ahead and do it. I think we have time. I'll let you guys go ahead and do it. Like, how would you calculate the total? I think where this would be difficult is if I didn't walk you through how to first do it for CO2. So if I had just given you this image and said, here are the initial pressures before the valves are opened, after we open the valves, calculate the total pressure in the entire system. That might have been a little bit daunting. Since we've already calculated CO2, I want you guys to go ahead and calculate the pressure of H2 and of argon, and then tell me what the total pressure is. So I didn't show the work for H2 and argon. It is the exact same thing as for CO2, just now plugging in the pressure and volume for H2, the initial pressure and volume. The V2, the final volume, is the same because the whole container is 4.5 liters. So each gas is filling out into that 4.5 liters. So we're going to find the individual pressures of each one and then add them together. That is the only way you could do this problem. You're just not given, adequate information to solve it any other way. Because you don't have the number of moles. You don't have the temperature. You have to rely on those individual gases to then give you the total. Okay, questions on this one? Are we all engaged? Okay. I feel like I'm not as engaged if I'm sitting down. It kind of drives me nuts. I could just stand up and deal with it. Lean over. That'll work. We'll just do this. Okay. So let's scroll up one and just kind of wrap up one more point about partial pressures and mixes of gases. So in this one, I use the air example. It's interesting because they actually give us this by volume, percent by volume, which we could kind of play with that as well, but I'm not going to bother. Let's pretend that this is moles, okay? So I'm going to get rid of that for now and just say moles of gas. All right, so if I have this idea of Dalton's law, total pressure equals the individual pressures. If I know temperature and volume, what I can do, because remember, temperature and volume would not be different for each of these gases in a mixture. If I'm talking about like the classroom, let's close the door and say this is our volume of the classroom, and it's got oxygen and nitrogen and argon and CO2 in it, and I close the door, that's a given volume, okay? Every single gas is going to behave like that volume. Same thing with the temperature. Each gas doesn't have its own temperature. They all have the same temperature as whatever is in the room. Okay, so what we can do is we take PV equals nRT, solve that for pressure. So let's say actually even add subscripts right now. So like let's say pressure of A and moles of A, because volume and temperature are for the whole container. R is a constant. So if I want to know the pressure of A, I can divide by V and get NA/RT over V, okay? NA meaning like the moles of whatever compound A is. So CO2. So the pressure of CO2 would be equal to the moles of CO2 times RT over V. Well, if T and V and R obviously are the same for every component of this mixture, you can actually pull that out, like factor it out. And now what you hopefully realize is that the pressure is really just dependent on the number of moles there. Like the pressure of each gas is going to be dependent on the number of moles of each gas. And so we can just sum up the moles of gas. Instead of summing up the individual pressures, if we know T and V, we can just sum up the moles of gas, and then we would be able to calculate the total pressure as well. Now, we couldn't do that in the previous problem because we didn't have temperature and volume. We had to rely on that change. But if we had that, we could just rely on the moles of each individual gas. So what's maybe a little bit interesting from that is that what we're saying is that a mole of CO2 behaves the same as a mole of water, which behaves the same as a mole of oxygen. Like the identity of the gas, at least according to the ideal gas law, the identity of the gas doesn't matter. It only matters how many moles of it you have. Even if you have like helium, that's a single atom, versus CO2, that's 3 atoms, right? They're still going to behave the same as far as how they affect the pressure, based on the number of moles of the gas, whether that's an atom or a molecule. Now, that definitely is an assumption. I just realized I'm missing a button. That's unfortunate. Distracted. That really is dependent on if they follow the ideal gas law. So we're going to talk about when do things follow that and when do they not. We're getting there. Okay? So that's pretty much as far as we're going to go with Dalton's law. There is more stuff. So there is one of the examples the textbook uses is experiments that are conducted over water. So a lot of the time we'll have experiments and they'll be producing a gas, like let's say hydrogen or something, or CO2, but it's collected over water because we like bubble the reaction through water, or maybe it's a solution and it produces the gas. So the problem is some of that water vapor gets included in the pressure measurement. So that's where we'll have to apply Dalton's law. We have to get rid of that water contribution in order to know what's actually coming from the gas. I just decided to kind of cut those examples out because we only have so much time. So that's a good reminder that as you're studying for the exam, That's coming on Friday. Did everybody remember that? Okay, so 6 is done today. Homework for 6 is tomorrow. Finish tomorrow. And then Wednesday and Thursday is your study time. So we will have review time on Wednesday. You can do the practice exam, bring any questions you want, or just questions from whatever, the notes, the textbook, and then exam on Friday. And you can all wear your costumes if it makes you feel better. I hope that's not, well, maybe, whatever. If it's your thing, that's great. Even my 7th grade daughter is like, no, I'm not wearing my costume to school. Yes, I'm still going trick-or-treating because I want candy, but I'm not wearing my costume. Okay. So, the last thing we need to, oh, no, that's not. There's 2 more things up here. I almost forgot. Okay. So one last thing we need to talk about related to actual calculations is standard temperature and pressure. So chemists like to assemble tables of information. So they'll have lots of different compounds and then they'll have like a piece of it. So it's like density and then they have densities for everything. Well, guess what? Density changes with temperature because things expand and contract and so their volume isn't consistent. So when we tabulate densities, we have to pick a particular temperature. So 25 degrees C is a common one. It's like a warm room temperature, something like 78 degrees Fahrenheit, but I don't know, it's a nice round number. So we pick 25 degrees C a lot of the time for that stuff. So they're not gonna give you a table of density at all these different temperatures. Maybe for water they might, but for like all these different compounds at all these different temperatures, they set what they call a standard temperature. So for density, that happens to be 25 degrees C. For gases, when they tabulate stuff like that, they set it at 273 or 0 Celsius and 1 atmosphere pressure. Why 0? I don't know. Gases are, maybe you get less things in the gas phase at that point, so it's easier to deal with. I don't know why. But lots of stuff like gases will behave, they're still moving around really fast. Whereas like when you're talking about a solid or a liquid, you really start to, in our real world where water is a big component, you know, you've now, maybe that's why, because at that temperature, you're not getting water vapor mixed into that. That would be a really good reason. Okay, so 0 degrees Celsius, 1 atmosphere pressure. That's what we decide is standard temperature and pressure. You have to know those. I'm going to say at STP, and you need to know that that means 273 K and 1 atmosphere pressure. Okay? Let me look at this picture for a second first. All right, so we take those numbers of 273 K and 1 atmosphere of pressure, and we develop this thing called molar volume, which just means the volume at 1 mole at STP. Okay? The reason why it's useful for someone that's working with this frequently is when you calculate this, you get a particular number, 22.4. Here's how you would do that calculation, right? Ideal gas law, plugging in for 1 mole, temperature at STP, pressure at STP, and you get 22.4 liters. Okay, that's kind of big. So 1 atmosphere is atmospheric pressure. 273 is colder than where we're at right now. And 1 mole of gas, so think of water, 1 mole of water. Let's see, I did this in my head the other day. It's like slightly more than a tablespoon of water, okay? 18 grams, which is about 18 mils. Yeah, it's like a little bit more than a tablespoon of water is a mole of water. So if I have that same tablespoon of water, now water's maybe not a great example because it's not going to be gas at 0 degrees C, but it's something we're familiar with. So if I were to take that tablespoon of water, it would be even bigger if it was a higher temperature, so it's still good. And it's at 1 atmosphere of pressure and relatively cold. Let's say the coldest we can get it while it's still in a gas. And it's just that 1 little tablespoon. It's going to fill 22 liters. So that is like more than 5 gallons. So 5 milk jugs. and it's going to fill that big space. So gases are very, very spread out. The particles are very spread out. Okay? So the other thing that's a little bit interesting with that is that it's the same no matter what the gas. Just like we talked about before, it doesn't matter if you have a mixture of gases, they're all going to behave independently and they're all going to behave the same. The same thing holds true here. If you have 1 mole at STP, they're all going to have that same volume of 22.4. So someone that works with gases frequently is going to have that number in their head, the 22.4, and then all they have to do to figure out whatever the other number of moles, like let's say it's, I don't know, 2.3 moles of gas, they just need to take 22.4 times 2.3 because every mole is going to be 22.4 liters. So they just can do a quick calculation. Instead of plugging into PV equals nRT, like you could do that, you could say volume equals 2.3 moles times R times 273K over 1 atmosphere. But it just prevents them, I mean, that's pretty much something you could do in your head, 22.4 times 2.3. Okay? Or at least roughly do the calculation. Yeah.
I'll read the question, because when I study the gases, all the container is, all the container are bottom. Can we use another, instead of bottom, another like container, like for example, this bottom?
Uh-huh.
Is it possible to use this container?
It would be a different volume though. Yeah, so that's fine, but it just would be a different volume. So you could do that, but you would then be dictating the pressure. So if we tried to squeeze a mole of gas into that, which is rigid, right? So it would hold that, it's going to be really, really pressurized. So it's all about, are you changing the pressure or are you changing the volume or are you changing the temperature? The other way we could get it down to a cooler, or sorry, I just gave it away. The other way we could get it down to a reasonable pressure like 1 atmosphere is we'd have to cool it down a ton so that the gas particles are moving more slowly. Yeah. And like, maybe I've mentioned this before, but you can even tell that like a soda can feels differently in the fridge versus outside. Like you can feel the tension, you can feel the increased pressure on it when it's in a warmer condition. Okay, so let's pretend that you don't remember the 22.4 and it's like calculate the volume of 2 moles of gas at STP. It's fine. If you remember 22.4, you just multiply it by 2, 44.8, right? If you don't remember it, just plug it into PV equals nRT. The thing you have to remember is what is STP? 1 atmosphere of pressure, 273 Kelvin. Okay? All right. Now the last thing. Okay. So all of this stuff that we've done, all of these calculations that we've done are dependent on assumptions from the kinetic molecular theory. So kinetic molecular theory is like, how do gases behave usually in the conditions that we're used to experiencing? And we're going to set some assumptions that tell us how they behave. And then most of the time, that should mean that our calculations will work. So these are the assumptions. We're going to go through them, and then we're going to talk about when does this break down. So the first one, the size of the particles is assumed to be 0. That seems a little weird. We're basically saying the matter that makes up the hydrogen gas or the oxygen gas or whatever doesn't matter. It doesn't play into it. It's like it doesn't exist, that volume that it takes up, okay?
This is for real or ideal gases?
For ideal gases, yeah. So this is ideal gases. So is that a good assumption? Well, we just talked about a tablespoon of water filling like a 5-gallon area. Okay, so the amount of water that's actually in that is pretty darn small compared to that entire thing. I mean, we could figure out a tablespoon is like a 1/16 of a gallon. So now we're talking about 1/16 out of 16 times 3. So it's 1/50th or 0.02% of the volume. Okay, it's a very small amount, And that's why it's okay to assume that it's 0, is because in that container, it doesn't actually contribute a whole lot, so it's not going to change our answer a whole lot. So this is maybe even more important with big containers. So if your volume is relatively big in comparison to the size, or as we're going to find out in a second, when are these assumptions good? When the particles are small. So if I have helium, right, that's like a very small gas, teeny tiny atom, that's probably a pretty good assumption to say it's close to 0. When I start to get into a really big molecule, like how about xenon tetrafluoride? That is a pretty darn big molecule. Number one, might not be a great assumption for a particle that big, for a gas particle that big. Okay? So maybe by the time we get to something as big as xenon tetrafluoride, maybe the ideal gas law doesn't give us the right answer. Okay, second one is actually a very good assumption. There is some issues with this when we start to talk about bigger particles again, because their mass ends up altering this slightly. But it says that the average kinetic energy is proportional to Kelvin. So this is just a good scientific literacy thing to make sure you understand that when we say something's hot, we mean the atoms and molecules are moving faster. Okay? So when you're, a parent and your kid is like, why does it feel so warm outside in the summer? You can be like, because the sun's radiation is making the molecules in the atmosphere vibrate faster. And those vibrations are what makes it feel warm when they bump against your body, because they transfer some of that heat. Doesn't that feel nice if you could say that to your child instead of being like, because it's hot, it's summertime? Okay, so this is a pretty good assumption. So we're not going to actually have a lot of issues with that one. And then the last one, the collision of particles is elastic. What the hell does that mean? So you have gas molecules, and they're constantly bumping into each other in the container. They're bumping into the walls of the container. That's what creates pressure. But they're also bumping into each other. And so we're basically saying when they do bump into each other, they don't lose any energy. They don't slow down at all. They don't transfer that energy necessarily. They just kind of keep moving. So think of like billiard balls that are like knocking into each other. That's a fairly elastic collision. You don't lose a whole lot of energy there. You lose energy because of friction from the table, but not usually from the hitting itself. If you were to do like tennis balls that are squishier, those tend to lose energy to each other. And it's the same with atoms and molecules, especially if you change the temperature. So like if you've got, like hydrogen atoms or something moving around, when they bump into each other at a slow temperature, the interaction between this guy's nucleus and this guy's electron and vice versa, those can start to cause a bond to start. If they're moving really fast, that interaction doesn't happen because the energy of their motion just overcomes any of those attractions. Okay, so one time when this is going to be most accurate is at high temperatures. So we set up here small particles would make sense with this, and also large container volumes, because then the difference between the two is more significant. And then the collision of particles, as long as we're at higher temperatures, that shouldn't be as much of an issue, that assumption. And I'm sure I'm missing something. Okay, so these assumptions are good for, we just talked about small particles and high temperatures. Oh, and the low pressures, what that really means is not a whole lot of particles in a given space. So pressure, when we talk about it, we've got to incorporate moles and volume. So you could have a low pressure if you had a huge container with some particles in it. You could also have a decently low pressure if the container's smaller, but then you'd have to have a smaller number of particles as well. So it's like a ratio thing. Okay, So when we meet these conditions, PV equals nRT is good, and it'll give us the right answer. When we don't meet those conditions, or like high pressures and low temperatures, then we call them real gases, and whatever we get from PV equals nRT is not going to be the right answer. There are some like mathematical manipulations we can use to get the right answer. We're not going to mess with those. The Van der Waals equations. I think your textbook covers them, but I think I've taken all those questions out of the homework, so it's fine. So there are things we can do, but the regular PV equals nRT is not going to be good enough at that point. All right, that's it. Yep.
You know the dry ice,
Mm-hmm.
like subject to.
Yeah, see it like CO2. Mm-hmm.
That is a liquid between it's in this water.
So at atmospheric conditions, it will never be a liquid. So it sublimates, which is goes from a solid to a gas, which is why it's so useful, because you can use it in like shipping and stuff, and then it won't ever cause like a liquid mess. I think that it's pretty darn high pressures. I want to say it's like 20 atmospheres that it has to be high to get it into the liquid phase. Yeah.
Is it possible to put it like in the bottle?
In the what?
In the bottle. See the.
Yeah, but it wouldn't like to contain the gas, or yeah. You could like put a chunk of dry ice, cover it, and allow it to expand and fill and create a pressure. Yeah. All right. All done. Yep. Have we ever ended 7 minutes early? My goodness.